Okay, welcome back everyone. In this last video covering Newton's laws, we're going to be talking about forces that depend on time, and also we're finally going to discuss air drag or air friction. So in this case, we really are looking at the nature of frictional forces, and this time we're talking about fluid friction. Before we do that, we're going to take a moment to do a couple of practice problems related to what we did last time, and this is forces in circular motion with non-constant velocity. And so, for example, if we have a 40 kilogram child sitting in a swing supported by 3 meter long chains, okay? So here is the swing, and here is kind of a bad picture of the child. We'll do it like that, okay? So they're 40 kilograms, and it's supported by a 3 meter long chain. And if we know that the tension in, well, I guess there's two of them. The tension in each chain at the lowest point is 350 newtons. We want to find the speed at the lowest point and the force exerted by the seat on the child at the lowest point. Okay, so looks like we have a couple of variables, okay? We have if we think about the child, we're going to have basically two tensions going up, and that's essentially what the force will be exerting on the child, okay? So that's going to be just basically 700 newtons, but then to get the speed, we're going to have to incorporate the force of gravity and use the fact that 2 times the tension minus the force of gravity is equal to mv squared over r. Okay, and actually this is kind of a bad question because we don't know the speed at the lowest point, we just know the tension. But this is how we would set it up, and if I said, for example, let's say the speed is 10 meters per second, then we could plug that in and calculate, oh, actually we're trying to find the speed, sorry. So we would have 700 minus 40 times 9.8 is equal to 40 times v squared over 3. Then we could solve that for v. Okay, and so that turns out to be, so 392 divided by 40 times 3, whoops. And it turns out that this is about 5.4 meters per second. Okay, another example. A 900 kilogram automobile is traveling along a hilly road. If it is to remain with its wheels on the road, what's the maximum speed it can have as it tops a hill with a radius of curvature of 20 meters? Okay, so here's the automobile. I can talk today really, and it's got a mass of 900 kilograms, and we want to calculate the speed. And if we were to think about the forces acting on it, we would have the force of gravity, mg, and we would have the normal force, and that's pretty much it. And those two forces would conspire to give us the total centripetal force, and so we would have essentially mg minus F normal is equal to m v squared over r. Now, the key point here is that if it's just going to remain with its wheels on the road, then what we have is that the normal force goes to 0. And that's kind of a boundary condition because if it's going any faster than the speed that we're going to calculate, then the normal force basically disappears because it flies off the road. So that goes to 0, the m's cancel, and v turns out to be the square root of gr. So 20 times 9.8 is 196, and the square root of that is 14 meters per second. Okay, so the mass of the automobile is irrelevant. Okay, so let's take a moment and talk about non-constant forces. These are forces that can vary with time, so F is a function of t, forces that can vary with velocity, F is a function of v, and forces that can vary with position, F as a function of x. Now these guys we're going to get to in the next chapter when we talk about work. So now we're going to talk about forces that vary with time and forces that vary with velocity. Okay, so forces that vary with time, we need to review calc very quickly. So the derivative or differentiation is the tangent of a function, and that's d dt of f of t, if you will. And then integration is the area under the curve. And integration takes us from acceleration to velocity to position, whereas differentiation is position to velocity to acceleration. So integration is kind of saying, let's take this function, f of t, and here's t, and let's split up this function into a bunch of pieces. And each of these pieces is going to have a little area. So if this is f of t, the area is actually going to be f of t, so the height of the function, times the width, which we're going to call dt. And we're going to add up all of those f of t's times dt's. And when we do that enough times with a small enough interval, we call that the integral. So again, I'm not trying to go into detail on integrals right now. So if you want to look into that more, there's lots of resources out there. Okay, but this is pretty important. This is the power rule for integrals. Okay, so this just basically says that the integral of t to the n dt is t to the n plus 1 divided by n plus 1 plus c. Okay, so again, remember that if I take the derivative of this again, okay, d dt of t to the n plus 1 over n plus 1 is actually going to be n plus 1 t to the n plus 1 minus 1 over n plus 1. And we're going to get back to what we started with, which is t to the n. Okay, so the derivative and the integral are inverse operations. And then the other thing is the so-called definite integral is when we evaluate t to the n from 0 to t. Okay? All right, so as an example, let's take a function that is f of t equals 3 minus 0.5 t squared in newtons. And if the force is acting on a 0.2 kilogram particle for 3 seconds, what is the resulting velocity and position? So first of all, we need to find if this is the force. Okay, well, we're just going to consider a scalar version. Okay, a of t is going to be f of t over m from Newton's second law. So that means that we're going to have 15 t minus 2.5 t squared, and now we're meters per second squared. So all I've done is I've divided by 0.2. Okay, now if we want to get velocity, v of t is going to be the integral of a of t dt. So let's do that. Let's take the integral of 15t to the 1 minus 2.5 t to the 2 dt. And so that's going to give us, so t to the 1 is going to increase t to the 2. And then 15 is going to have to get divided by 1 plus 1, which is 2. Okay. Then we're going to have, let's call this 5 halves. Okay. T squared will turn into t cubed, and we divide 5 halves by 3 to get 5/6. And then we're going to add c to this, but we're going to assume that v of 0 is 0, and since each of these terms have a t in it, this means that c is 0. We'll call that c1. Okay, so that's gone. And v of t is just going to be this expression right here. Okay? Now, x of t, the position, is going to be the integral of v of t dt. And so that's going to be the integral of 15 halves t squared minus 5/6 t cubed dt, which is going to turn into, okay, we have t cubed, and then we'll have 15 over 6 minus t to the fourth, and then we'll have 5 over 24th. So hopefully you see the pattern. Well, we are also going to assume that we can add a c2, but we're going to say that c2 is also 0 because x of 0 will be set to be 0. So this will go away, and x of t is going to be 15/6 t cubed minus 5/24 t to the fourth. So then we can just evaluate each of these at 3 seconds. And so v of 3 is simply going to give us 45 meters per second. If you plug a 3 in there, you'll get 15 times 9 over 2 minus 5 times 27 over 6 will give us 45. And then x of 3, if you do the math on this, is going to come out to about 50.6 meters. So I'm not going to go through the details, but that's kind of how we set this up. Okay, let's do one more. So here's another force that is a function of time, and we want to find the change in velocity if we have a 4 kilogram particle, which this force acts on for 1 second. So we do pretty much the same thing. First we find the acceleration by taking f of t and dividing by the mass. So mass of 4 means that we're going to have 4t squared minus 2t plus 1 meters per second squared. And so to get the velocity, v of t is going to be the integral of a of t dt. So that would be the integral of 4t squared minus 2t plus 1 dt. And that's going to give us, remember our rule, t is going to increase to 3, so I'll have 4/3 t cubed, minus t is going to increase to 2, so I'll have 2 over 2, which is just 1, and then we'll have plus t. Remember that any time we have a constant, 1 is the same thing as 1 times t to the 0, because that's also 1. So t to the 0 becomes t to the 1, and since we're multiplying by 1, it's just t. Okay, so I would write this as 4/3 t cubed minus t squared plus t, and then this would be plus c, but again, we're going to say that this is at rest, so since there's no other constant terms in here, we would say v of 0 equals 0, and consequently c equals 0. So this is our velocity. So then the change in velocity will be v final minus v initial, but v initial is 0, so we just want our change in velocity is going to be equal to v final, which is going to be 4/3 times 1 cubed minus 1 squared plus 1. So it's just 4/3 meters per second. Okay, so we're going to stop here, and then we're actually going to have one more video where we're going to talk about air resistance and how that affects our motion in free fall.